Hello and welcome back to Math and Tea, a show where we talk math and drink tea. I'm your host, Dr. Joseph Van de Heij, and in today's episode we're continuing to discuss what is math by talking axioms. Now I'll warn you, this is where things start to get a little, weird. You see, in the last couple of episodes, the things I've been discussing have been different in emphasis more than anything else. You've seen these sorts of things before, but just not put in this sort of fashion. Now with axioms, things are going to change a lot. Math is going to look just, well, wrong. Now in the previous episode, I talked about how mathematics is about building up new truths from old truths using logical deduction. The truths you start with are your axioms, because you have to start somewhere, right? So if you're interested in reading up about it, most of mathematics is built up out of set theory, and set theory in turn is most commonly built up out of these Zermelo-Fraenkel axioms. Or maybe you add the axiom of choice in with these Zermelo-Fraenkel axioms. Now note that maybe. It's important because the axiom of choice can sometimes lead to some very annoying paradoxes, and so mathematicians don't always really like it. Now this all starts to sound very peculiar. After all, axioms are the foundations of mathematics. Shouldn't they be statements that are obviously true? Well, not necessarily, because if we change the axioms a little bit, we change the space in which we're working, and sometimes that's exactly what we want to do. Now let's consider a specific example. Geometry. Specifically the geometry of a flat plane, a sheet of paper that goes infinitely in all directions. Maybe you heard back in high school that all of geometry can be built up out of 5 postulates, or axioms, that date back to the great Greek mathematician Euclid. The first 4 of these postulates are quite elementary. Like the first one says that if I put 2 points on my plane, I can draw a straight line between them. Obvious, right? But the 5th one is a lot different. The 5th postulate is known as the parallel postulate, and it says something like this. If you've got a line, and you've got a point that's not on the line, then there is one and only one line that goes through the point that will never touch the first line. That one line looks a little bit like this. And you'll notice why it's called the parallel postulate, because this line is parallel to this one. These 5 axioms give rise to a very good geometry on a flat surface. But there's lots of other surfaces we want to do geometry on, such as a sphere. Now, on a sphere, straight lines are a little different. They're called great circles, and they divide a sphere into 2 perfect hemispheres, like the equator does on Earth, or any of the lines of longitude. But the thing about straight lines on a sphere is that you pick any 2 of them, and they always have to intersect. You can't get away from it. So the parallel postulate just, well, it doesn't work here anymore. We have to find something else, a different axiom, that does. Now, this gives some of the idea of why mathematicians change axioms around. We need certain axioms to study flat geometry and certain axioms to study spherical geometry. But it gives it a kind of a weird perspective, as if we're starting from the object and extracting the axioms needed to make it work in a logical fashion, when we don't have to. We can just start tweaking the axioms around a little bit until we arrive at a space that might not look like anything familiar at all. To illustrate this further, let's look at a common mathematical object, the field. And here I'm going to fudge a little bit between what is an axiom and what is a definition, okay? Now to begin with, a field has 3 parts. It has a set of numbers, or more generally, a set of elements, addition, and multiplication. And the first 3 rules that a field must satisfy are listed here, and they all look fairly familiar, right? These are the ways that we normally expect addition and multiplication to work. The first 3 rules state that a field should be associative, so that you can stick the parentheses wherever you want. It should be commutative, so order shouldn't matter. And multiplication should distribute over addition, just the way it normally does when you are normally multiplying and adding numbers. So far, so good. Now, here's where things get a little more complicated. The next 2 rules talk about identities. First off, we need that there's an element, which we denote by 0, that is the additive identity, so that if you add 0 to anything, you just get that thing right back. We also need a multiplicative identity, which we denote by 1, so that if you multiply 1 by anything, you just get that thing right back. The last rule there talks about the existence of inverses, but it's kind of not important for us at the moment. And of course, it's easy to think of an example of a field, because the common set of real numbers that you learned in school is a field. Now consider the following. Based just on the axioms that I've given here, what is 1 plus 1 in an arbitrary field? Don't worry, I'll wait. Okay, time's up. If your answer was, there's not enough information to tell, you'd be right. Just based on the axioms I've listed here, we have no idea if 1 has its usual meaning. All we know about it is that it's a number, such that if I multiply, whatever the heck multiply means, because I don't know what that does either, it to anything else, I get that thing right back. That's the only thing I know about the number 1. That's it. That's all. So far, all we know about elements in our field is that 1 and 0 exist in it. And so maybe 1 plus 1 is a new thing, and if it's a new thing, there's no reason why we shouldn't call that thing, well, 2. But maybe, just maybe, 1 plus 1 equals 0. Now, wait. You're going to think I've completely lost my mind on this, but remember, 1, 0, and plus don't have their usual meaning here. They're just objects that satisfy a certain set of axioms. And there's nothing wrong with those axioms to also say that 1 plus 1 equals 0. So let's do it. So let's assume we have a field. And let's further assume that in this field 1 plus 1 equals 0. And for simplicity's sake, let's also assume that there aren't any other elements besides 0 or 1. So we have a field with just 2 elements in it. And its addition and multiplication tables look like this. Now this all looks crazy and weird and some sort of strange mathematical nonsense until I make one little change. If I replace every copy of 0 with even and every copy of 1 with odd, then I get precisely the tables that tell me what happened when I add or multiply even and odd numbers. And this isn't just an accident either. This is really why it works. So this weird system with its strange and unnatural rules nonetheless tells us some useful mathematical information. Sometimes we mathematicians just love breaking all the rules, but I hope this has convinced you that there is a bit of sense lurking behind that mathematical nonsense. I'd love to tell you more about how a real-world problem becomes a strange, abstract mathematical problem, but it'll have to wait till next time because, I'm out of tea again.